Well, thanks for inviting me, and sorry I can't be there in person. So my talk is on the North Atlantic Hosing Model Intercomparison Project, which is a project I've been leading for the last few years with a lot of help from all these people.
So, Laura, just for your information, the sound is pretty low and I'm not sure how to raise it, so don't hesitate to speak loud.
Okay, I'll try and get nearer the speaker. Okay, so the abbreviation is NAHosMIP. That's what we're calling the project. And the aims are to examine the AMOC thresholds and CMIP6 models in the presence of freshwater forcing, particularly thinking about, is there a threshold beyond which the AMOC doesn't recover? So we wanted to understand whether the CMIP6 models exhibit a threshold in the AMOC and understand how different feedbacks contribute to the different behavior in different models. And then ideally what the implications of this are for the real world. So we had 8 CMIP6 models of varying resolution and ocean component. And we have a published paper of the experimental protocol and initial results, which is listed here. And we have, and I'm writing up a second paper looking at the mechanisms. So the main experiments I'm going to talk about are these experiments we called U03. So we wanted to use large idealized hosing to help understand model sensitivities and how they differ. And we wanted to use uniform distribution to target models with different regions of deep convection. So we applied hosing over this yellow region. So the hosing experiments, we're applying 0.3 sphere drops of fresh water. And then we have those recovery experiments where we stop the hosing, we spin off experiments with no hosing after 20 years and 50 years, and then also 70 or 100 years. So here are the sort of the main results for the AMOC. So the black lines here, these are the 8 different models we used, and there's the black lines show the pre-industrial strength. The grey lines show the what happens in the hosing experiments. So in all the experiments, the AMOC weakens, as we'd expect. And then the blue and green lines show what happens when we stop the hosing. So you can see if you look at the bottom left-hand corner in the MPI model here, the AMOC always recovers even after 100 years of hosing. It recovers over, it's certainly shown signs of recovering over 50 years there. But then there are a number of experiments. There's these 4 different models rather, where there's an experiment where the AMOC stays in this weak state. So this, for example, CSM2 stays in this weak state for 200 years at least. So note we're saying I'm not going to refer to these as collapse because there's lots of different definitions of collapse. And it's not really an off state, it's a weak state. We haven't reversed the overturning. And obviously we can't say that these states are stable because we've only run them for 100, 200 years. So what is there something that's different between those models which reach that weak AMOC state and those which don't? And we spent quite a lot of time looking at this, and basically the summary is that we didn't find any consistent differences between those groups of models. So we looked at the ocean model type, the resolution, parameterizations of mixing. We looked at the deep convection, which is shown here in this plot. This is the March mix layer depth. And the models all have very different depths and extent and location of the deep convection. We also looked at biases in temperature, salinity, sea ice, stratification in the mean state. And then we did look at the freshwater transport by the AMOCs. This is FOV and MOV. And we didn't find any consistent differences between those models which reached this weak state and those which didn't. But one thing we did see which was different is not the actual models, but the states which are reached. So if we take the time series of the AMOC after we've stopped the hosing, and we plot them all here in years since the hosing stopped, you can see these dashed lines at the bottom are the ones the AMOC has reached a really weak state during hosing, and then it stays in that weak state. Whereas the models which have only maybe got down to 10 sphere drips, the AMOC then recovers once the hosing stops. But it's not just about the AMOC. So we also looked the plot at the bottom shows on the x-axis, it shows the total mixed volume of deep convection. And these 4 circles in the bottom left-hand corner are the experiments where the AMOC doesn't recover. So you can see not only do they have a weak AMOC once the hosing stops, but they basically switched off that deep convection. And that may be more physically relevant than the actual strength of the AMOC. So I'm going to focus a bit more now in these 2 different models, these 2 different MetOffice models, LL and MM. And these basically differ in terms of the resolution, but they also differ in terms of the mean state, which is caused by the differences in resolution. So this is looking at the AMOC in density space in the control and then in the hosing experiments. And you can see that at the end of the hosing experiments, the LL model still has, some significant hosing, some significant overturning going on there. Whereas the MM model, there's basically no overturning in density space anymore. And we can use something called water mass transformation theory, which I'm not going to get into. But basically, you can look at the surface fluxes, and you can calculate what they imply the overturning should be. And this is shown on the left here. So in the LL model, those surface fluxes are implying still that there's a significant overturning, whereas in the MM model, they're implying no overturning. And if we can look at where those fluxes are occurring, you can see that in the LL model, they're basically occurring in the ginces. So in the LL model, the overturning is being sustained because of surface buoyancy fluxes in the ginces. And then this is looking at the mean states of after 100 years of hosing in the 2 models in a bit more detail. And on the left, you can see the surface buoyancy flux and the ice extent. And then on the right, the surface density, which is the coloured surfaces, and mixed layer depth, which are the contours. And you can see that the MM model at the bottom has lighter surface waters. It has less buoyancy flux, which basically means there's less heat loss. There's a lot more sea ice, and there's a lot shallower convection. And this all fits with the fact that it doesn't have the same water mass transformation, the same overturning. And we can extend this to looking at all these 8 models. So the ones in the top here are the ones where the AMOC recovers, and you can see they all have, still have relatively dense surface waters, and they all have some deep convection going on. Whereas in the bottom, you can see that they're generally lighter surface densities and less mixed layer depth, less convection. So I'm not going to go into this in too much detail, but we looked in the MetOffice models a bit more at what's actually happening in the ginces. But we see signs of like a convective feedback, where when you have strong convection, it brings warm, salty water up to the surface, which encourages more heat loss and then more convection. And we also see importances of ice cover. So when we have large cover ice over the ginces, then there's less heat loss to the atmosphere. One thing we see, excuse me, one thing we see which it seems to be quite important is the heat transport. So this is showing the heat transport by latitude in the 8 different models. In the left, it's showing the control heat transport, and then the middle and the right are the anomalies after 50 and 100 years. So as you expect, after hosing, when the AMOC weakens, we get less heat transport. So we see this weakened heat transport. However, if you look at high latitudes, you can see there are some models here after 50 years which actually have an increase in the heat transport. And after 100 years, they have maybe a slight increase, but certainly not much of a decrease compared to some of the other models. And these are all the models which you can see are like blue and green colours. And those are all the models where the AMOC weakens a little and then it recovers. And so they all have an increase or little change in heat transport into the ginces after hosing. Whereas the models where the AMOC weakens more and stays in that weak state, which are the yellow, orange, red, and pink models, they have a reduction in heat transport into the ginseeds after hosing. And this may be important because the heat transport into the ginseeds, obviously if you have more heat transport, that's going to inhibit the sea ice forming and encourage the convection and water mass transformation. So obviously the next question is, why is there a difference in the change in heat transport? And the short answer is don't really know. This is looking at the anomaly in the barotropic stream function after hosing. So in the two MPI models here, you can see that you see there are blue blobs here, which basically means we have a stronger subpolar gyre, which could be transporting more heat into the ginseeds. But we don't see the same in these other two models here. They do have a stronger subpolar gyre in the ginseeds, but then so do two of the other models where the AMOC, where the heat transport weakens strongly. So the answer is we're not really sure about that. So conclusions. So at least some CMIP6 models have the potential to reach a quasi-stable weak AMOC state. So when I say stable, for at least 100 years after weakening from hosing. And the ability to reach this weak state depends on how weak the AMOC gets during hosing, but maybe more physically relevant is the ability to reach a state where there's no longer deep winter convection in the ginseeds. And there's a number of processes and feedbacks which are important, but possibly the most important for distinguishing the response is the transport of heat into the ginseeds. So thank you. Are there any questions?